What happens when the laws we trust begin to tremble? Not in theory, not in myth, but in the quiet, fluorescent light of a laboratory where instruments hum and numbers appear on screens with no sense of drama at all. Science is often imagined as a fortress of certainty, built stone by stone through measurement, repetition, and proof. And yet, every so often, a crack appears in the wall. Through that narrow opening, something stranger comes into view. This story begins in those cracks. In experiments designed to confirm what we thought we knew, researchers sometimes found the opposite. Results that seemed to mock common sense, unsettle causality, and blur the clean border between observer and world. A particle behaving as though the future mattered. Empty space acting as if it were full. A system that seemed to remember, to respond, or to move in rhythms that should have been impossible. These moments did not arrive with thunder. They arrived as anomalies, small enough to dismiss, powerful enough to linger. The history of science is, in part, the history of such discomfort. Again and again, reality has refused to fit neatly inside the language built to describe it. The Earth was not the center. Time was not absolute. Matter was not solid. Each revelation humbled us. Each forced us to trade certainty for a deeper, stranger form of understanding. So this is not a tale of physics failing. It is a tale of human beings standing at the edge of knowledge, watching familiar ideas loosen their grip. Across 10 extraordinary experiments, we will follow that uneasy frontier where discovery becomes doubt and doubt becomes wonder. Because the most haunting possibility is not that the universe is broken. It is that it has always been more subtle, more layered, and more alive with mystery than we were prepared to see. What if the first crack in certainty came from light itself? In the early years of the 20th century, physicists believed they were closing in on a complete description of nature. Matter could be weighed, motion could be predicted, and light, though mysterious, seemed at least familiar. It traveled in waves. It illuminated surfaces. It revealed the world without appearing to disturb it. Then, a deceptively simple experiment began to suggest that light was not merely showing reality to us. It was participating in it. Imagine a darkened room, a barrier cut with two narrow openings, and behind it a screen waiting quietly for impact. Shine light through one slit, and the pattern on the screen makes sense. Open the second, and a new image appears, alternating bands of brightness and shadow, as if light were not a stream of tiny projectiles, but a wave interfering with itself. This alone was strange enough, but the deeper unease arrived when physicists sent particles one at a time, expecting each to choose a path like a grain of sand tossed through a window. Instead, the same wave-like pattern slowly emerged, dot by dot, as though each particle had somehow traveled through both openings at once and met itself on the other side. And when researchers tried to measure which slit the particle passed through, the interference vanished. The act of observation seemed to alter the event itself. Reality, once imagined as a stage proceeding independently of the audience, now appeared to shift when someone looked too closely. No one had intended to shake the foundations of physics with a pair of slits in a screen. Yet that is what happened. The experiment did not destroy the laws of nature. It revealed that those laws were written in a language more elusive than anyone had expected. Beneath ordinary experience lay a world where possibility preceded fact, and where certainty arrived only at the moment it was forced into view. That was the beginning of a long and unsettling lesson. The universe was not simply waiting to be observed. Somehow, In ways we still struggle to name, observation had become part of the story. What if emptiness was never truly empty? By the middle of the century, physics had already learned to live with paradox. Particles could behave like waves. Observation could influence outcomes. But even then, there remained one quiet assumption that seemed safe enough to keep, that a vacuum, stripped of matter and light, was a kind of clean silence, an absence, a blank page in the book of reality. Then came an experiment so delicate it felt almost poetic. Two metal plates were placed extraordinarily close together inside a vacuum, near enough that nothing visible seemed to pass between them. No wire connected them, no magnet pulled at them, and yet the plates drifted toward one another, as though some invisible hand had pressed lightly on both. The effect was tiny, almost embarrassingly small, but it was real. It could be measured, repeated, confirmed. What moved them was not matter in the ordinary sense, but the restless character of space itself. In the quantum view, emptiness is not still. It trembles with fleeting activity, with fields that cannot fully settle into silence. Virtual particles appear and vanish below the threshold of direct sight, like murmurs in a room we thought was vacant. The narrow gap between the plates altered that hidden activity, and the imbalance created a measurable force. The vacuum was doing work. It is difficult to overstate how unsettling this was. The old intuition said that nothingness should do nothing. But here was an experiment suggesting that what we call empty space is not a passive backdrop. It has texture, pressure, possibility. The void is not a void at all. It is a sea whose waves are too small and too brief for the senses, but not too small to shape reality. For centuries, human beings feared emptiness as loss, loneliness, or erasure. Physics offered a stranger image. The spaces between things are not dead gaps in creation. They are alive with hidden motion, a quiet abundance concealed beneath apparent stillness. And if even nothing is full of consequence, then perhaps the universe is telling us something profound. Absence is often only another name for what we have not yet learned how to see. Can two things touch across distance without anything crossing the space between them? That question once belonged to superstition, to folklore, to the human habit of sensing hidden threads in the world. Physics had worked hard to remove such ghosts. Forces should have carriers. Causes should travel through space in lawful ways. Nothing should whisper to something else from afar without a path connecting them. And yet, in experiment after experiment, a phenomenon emerged that sounded less like engineering than enchantment. Two particles interacted and then separated. Sometimes they were carried to opposite ends of a laboratory, sometimes imagined at opposite ends of the cosmos. Measure one, and the other seemed to answer instantly, as though distance had become irrelevant. Not because a message traveled faster than light, but because, at some deeper level, the two were no longer fully separate things. This was entanglement, a word so tidy it barely prepares us for its implications. Einstein famously disliked it, calling it a kind of spooky action because it offended his sense that reality should be local, orderly, self-contained. But experiments continued, becoming sharper, cleaner, harder to dismiss. Again and again, the results favored a universe in which relationships can be more fundamental than location. What mattered was not just where a thing was, but how it had once been joined. There is something deeply human in the discomfort this causes. We spend much of life trying to define boundaries, self and other, here and there, now and then. Entanglement suggests that, beneath those useful divisions, the world may be woven more tightly than our everyday minds can tolerate. separation may be real in one sense and incomplete in another. Physics did not prove mysticism. It did something more demanding. It showed that reality itself may resist the neat independence we prefer. Objects can carry histories of connection that survive distance, and those histories can shape what becomes visible when we finally look. Perhaps that is why entanglement feels so haunting. It reminds us that the universe may not be built from isolated pieces after all, but from bonds we barely understand and cannot entirely break. What if time itself did not move with the steady confidence we assign to clocks? For most of human history, time felt like the most reliable thing in the world. It carried rivers to the sea, children into age, stars across the sky. Even when physics began to unsettle matter and light, time still seemed like a fixed stage on which the drama unfolded. Then came experiments precise enough to reveal that time was not the stage, it was part of the performance. At first, the idea seemed almost too strange to deserve belief. According to relativity, motion and gravity could alter the rate at which time passed. A clock on a mountain would not agree perfectly with one at sea level. A clock carried at high speed would return slightly out of step with the one left behind. These were not metaphors. They were measurable effects, small in ordinary life, undeniable in the laboratory. Atomic clocks confirmed it with astonishing fidelity. Time, once treated as universal, had become local, elastic, vulnerable to circumstance. The consequences reached far beyond theory. Satellites circling Earth had to account for these distortions, or our navigation systems would drift into error. The modern world, with its maps, networks, and invisible timing signals, depends on a truth that would have sounded impossible to earlier generations: that different parts of reality experience duration differently. There is no single master clock keeping perfect order for everyone, everywhere. This realization carries a quiet, emotional force. We speak of wasting time, saving time, running out of time, as though it were a single substance, shared equally by all. Physics offers a gentler, stranger image. Time is not a rigid river flowing the same way for every witness. It bends around mass, stretches with motion, and clings to the circumstances of the observer. And once that becomes clear, something deeper shifts. If time can slow, warp, and diverge, then our experience of reality is not merely incomplete, it is situated. We do not stand outside the universe measuring it from a safe distance. We move within it, and even the ticking of our clocks is part of the mystery we are trying to understand. What if the universe could decide the shape of the past based on a choice made in the present? Few ideas sound more offensive to common sense than that. Cause should come first. Effect should follow. Time should move in one direction, carrying events forward like a current. But one of the most unsettling families of experiments in modern physics suggested that, at the quantum level, this sequence may not be as secure as it feels. In delayed choice experiments, particles are set in motion before researchers decide how they will later be measured. The question is deceptively simple. Did the particle behave like a wave spreading across multiple paths, or like a localized object taking one route? Classical intuition says the answer must already exist before the measurement is chosen. But the experiment says otherwise. The setup selected at the last moment appears to influence which history becomes visible. It is as though the particle keeps its options open until the world asks a more precise question. This does not mean the past is rewritten like a page torn from a notebook. Physics remains careful here. What changes is not history in the human sense, but the kind of story nature allows us to tell about what happened. Still, that distinction does not fully quiet the unease. The line between event and interpretation, between what was and what can be known, begins to blur. For centuries, people imagined knowledge as a lamp carried into darkness. The world was already there, complete and waiting. An observation merely revealed it. Delayed choice experiments suggest a more intimate arrangement. The questions we ask are not passive beams of light. They help determine the form in which reality answers. That possibility has a haunting elegance. It does not make the universe irrational. It makes it relational, responsive in ways that challenge our oldest habits of thought. Perhaps the world is not a finished archive waiting to be opened, but something more alive than that, something that meets inquiry halfway. And if that is true, then understanding reality may require more than collecting facts. It may require accepting that the act of seeking is woven into what is found. Can a thing be in two states at once and still belong to the ordinary world? For a long time, superposition sounded like a rule reserved for the very small. Electrons, photons, the hidden machinery of the quantum realm. It was strange enough there. A particle could exist as overlapping possibilities until measurement pressed it into a single outcome. But the deeper question lingered like a challenge no one could quite ignore. Where exactly did that strangeness stop? To explore it, physicists began building experiments of extraordinary fragility. They cooled systems towards silence, isolated them from heat and vibration, and coaxed larger objects into behaviors once thought impossible outside textbooks. Superconducting circuits carried currents that seemed to flow in more than one direction at once. Molecules passed through interference setups as though they, too, could inhabit multiple paths. These were not abstractions anymore. Quantum ambiguity was being engineered into objects big enough to edge toward the border of everyday intuition. The challenge was never simply to create superposition, but to preserve it. The world is noisy. Light, temperature, stray interactions with the environment all conspire to force possibilities into decisions. This process, known as decoherence, is both technical and philosophical. It explains why the macroscopic world seems stable and singular, why chairs do not flicker between locations, and why people do not experience themselves as clouds of probability. The classical world may not replace the quantum one. It may emerge from its collapse under the pressure of constant contact. There is something almost tender in that realization. Reality, at its deepest level, may be full of openness, multiplicity, and suspended outcomes. What we call solidity could be the hardened crust formed when that openness meets the endless touch of the world. Certainty, in this view, is not the starting point. It is what remains after possibility has been worn down. And so the question becomes larger than physics. Perhaps many things appear fixed, not because they were always simple, but because complexity has settled into form. Beneath the surface of the familiar, the universe may still be shimmering with unfinished options, waiting at the threshold where mystery becomes matter. What if a particle could tunnel through a wall it had no right to cross? In everyday life, barriers are among the simplest truths we know. A ball thrown at a brick wall stops. A locked door keeps a room sealed. Obstacles divide the possible from the impossible. But deep in the quantum world, that certainty begins to soften. And experiments revealed a phenomenon so improbable it first sounded like an error in language. Particles, under the right conditions, could appear on the far side of an energy barrier without ever possessing the classical energy required to climb over it. This became known as quantum tunneling, though the word tunnel is almost too concrete for what occurs. Nothing is drilled out. No hidden passage is carved. Instead, the particle exists as a spread of possibility, and part of that possibility extends through the barrier itself. Most of the time, the barrier wins, but not always. Occasionally, on the other side, the particle is simply there. What classical physics forbids, quantum mechanics permits with a certain quiet shrug. This was not a rare curiosity tucked away in equations. It proved essential to the architecture of reality. Tunneling helps power the nuclear reactions inside stars, including the sun that warms our skin each morning. It allows modern electronics to function at scales where classical rules would fail. Even radioactive decay carries this strange signature, as particles escape atomic nuclei through a process that resembles improbability made routine. There is something deeply moving in that. The universe does not always obey the hard edges our intuition prefers. Sometimes it advances not by force, but by subtle permission. A boundary remains real, and yet it is not absolute. Matter finds a way through, not because the rules are broken, but because the rules themselves are more generous and more mysterious than common sense imagined. Perhaps that is why tunneling stays with us as more than a scientific fact. It suggests that barriers, even the most convincing ones, may not be the final word. At the smallest scales of existence, possibility does not end where certainty says it should. It lingers, presses forward, and sometimes passes through the dark as if the wall were never as solid as it seemed. What if the deepest challenge to physics came not from distant galaxies or abstract equations, but from the simple fact that measurement itself has a cost? By the late 20th century, scientists were no longer shocked that quantum systems behaved strangely. The surprise now was how stubbornly that strangeness resisted capture. The moment a system was measured, its delicate uncertainty seemed to vanish. Possibilities narrowed. A choice appeared. And whatever hidden richness had existed just before observation was gone. This tension became more than a philosophical puzzle when researchers began building technologies that depended on preserving quantum behavior. In laboratories around the world, ions were trapped, atoms were cooled, and qubits were coaxed into fragile states of coherence. The goal was not merely to observe the quantum world, but to keep it alive long enough to use. Yet every attempt exposed the same paradox. To control such systems, one had to interact with them, and interaction itself threatened to destroy the very phenomenon being controlled. Experiments in quantum error correction and weak measurement offered a new kind of insight. They showed that information could sometimes be gathered gently, partially, without forcing an immediate collapse into classical certainty. It was as though reality could be touched with a lighter hand. Not fully possessed, not fully pinned down, but approached. This did not solve the mystery of measurement. It made the mystery more practical, more intimate, woven into the future of computation, communication, and our most ambitious attempts to engineer the unseen. There is something profoundly human in this struggle. We want knowledge that is clear, stable, and complete. But nature keeps reminding us that perfect access may be impossible. To know a thing is often to change it. To preserve its subtlety, we must accept limits on how firmly we can grasp. That lesson reaches beyond the laboratory. Some truths may only survive under conditions of restraint, patience, and humility. The universe does not always yield itself to force. Sometimes it asks for a softer form of attention, one that understands the difference between watching and overwhelming, between learning from reality and demanding that it become simple enough to satisfy us. What if the universe allowed information to hide in plain sight, scrambled beyond recognition, and yet never truly destroyed? This question emerged with new urgency when physicists turned their attention to black holes, those regions of space where gravity becomes so overwhelming that escape itself seems impossible. Classical intuition offered a severe answer. Anything falling in would be lost to the outside world forever. But quantum theory, with its deep resistance to erasing information, refused to accept such a clean disappearance. The tension sharpened when Stephen Hawking showed that black holes are not entirely black. Through quantum effects near the event horizon, they can emit radiation and slowly evaporate over immense spans of time. It was a breathtaking result, one that joined gravity, thermodynamics, and quantum physics in a single, uneasy frame. Yet it carried a devastating implication. If a black hole could evaporate away, what happened to the information contained in everything it had swallowed? Was it destroyed, leaked out in disguised form, preserved somehow at the edge of oblivion? This became more than a theoretical debate. It was an experiment of the mind, driven by mathematics so powerful that many physicists felt the foundations shifting beneath them. If information could truly vanish, then quantum mechanics itself might be incomplete. But if it survived, then our ideas about space, causality, and interior reality might need to be rebuilt. Over time, more and more evidence suggested that information is not lost after all. It may be encoded in ways almost unimaginably subtle, spread across horizons, correlations, or deeper structures not yet fully understood. There is something deeply haunting in this conclusion. Nature may permit disappearance, but not annihilation. What falls beyond reach may still remain written somewhere in the fabric of the world, not erased but transformed beyond ordinary recognition. Loss, in this picture, is real to the observer and yet incomplete in the larger accounting of reality. And perhaps that is why the black hole paradox continues to resonate beyond physics. It speaks to a human fear older than science itself, that what passes away is gone, without remainder. The universe offers a gentler, stranger possibility. Perhaps nothing meaningful is ever simply deleted. Perhaps it is hidden, folded inward, waiting for a language subtle enough to read what darkness has preserved. What if the vacuum, the particle, the clock, and the black hole were all pointing toward the same hidden truth? By now, the pattern is impossible to ignore. Again and again, experiments that began as narrow technical inquiries opened into something far larger. Light behaved as both wave and particle. Empty space revealed pressure and motion. Distant objects remained linked in ways that defied ordinary separation. Time bent. Measurement interfered. Information refused to die. Each discovery seemed different on the surface, yet underneath them all ran the same quiet disturbance. Reality was more relational, less solid, and more context-dependent than physics had once imagined. This convergence changed the emotional landscape of science. Earlier generations often pictured progress as a march toward final clarity, a gradual clearing of fog until the machinery of the universe stood fully exposed. But the deeper physicists went, the less the world resembled a machine made of separate parts. It began to look more like a web of conditions, probabilities, and hidden symmetries where what something is cannot always be separated from how it is approached, measured, or connected to everything around it. That realization did not weaken science. It matured it. The most powerful experiments were no longer those that simply confirmed expectation, but those that forced humility. In that sense, the laboratory became not just a place of control, but a place of encounter. Instruments were refined, equations sharpened, but the deeper achievement was philosophical. Human beings learned that nature does not owe us simplicity. It offers truth, but often in forms that exceed our instincts. There is a kind of dignity in that. To discover that the world is stranger than expected is not a failure of reason. It is reason doing its most honest work, following evidence beyond comfort and allowing wonder to survive the test of measurement. Perhaps that is the real turning point in every one of these experiments. Not the instant a result appeared, but the moment someone chose not to look away. And that choice still defines us. Faced with a universe that refuses to become small enough for certainty, we continue asking questions anyway, trusting that mystery is not the enemy of understanding, but its beginning. What do these experiments ask of us now? Not merely better equations, though those will come. Not merely finer instruments, though they too will be built. Their deeper demand is more personal than that. They ask whether human beings can live with a truth that does not always arrive in the shape of certainty. They ask whether knowledge can remain rigorous without becoming rigid, and whether wonder can survive inside precision. In laboratories today, the legacy of these discoveries is no longer confined to philosophical debate. Quantum computers are being assembled from the fragile logic of superposition and entanglement. Sensors of astonishing delicacy exploit the very fluctuations once dismissed as noise. The bending of time is corrected for in the systems that guide airplanes, ships, and phones across the planet. What once sounded like a challenge to common sense has become part of the infrastructure of ordinary life. The strange has become useful, and yet it has not become less strange. That may be the most beautiful aspect of science at its best. Explanation does not always diminish mystery. Sometimes it deepens it. To say that empty space seethes with activity or that particles remain correlated across distance is not to drain the world of poetry. It is to discover that poetry was hidden in the structure all along. The universe is not made smaller by understanding. It becomes more intricate, more intimate, more difficult to take for granted. And still, beneath every application and theorem, the old human questions remain. What does it mean to observe, to know, to inhabit a reality that is never fully independent of the ways we meet it? These are not only scientific questions. They are questions about humility, about perspective, about the limits of control. Perhaps that is why these experiments continue to echo beyond their data. They remind us that intelligence is not the conquest of mystery, but a relationship with it. We learn, we measure, we refine. Yet the horizon keeps receding, not as punishment, but as invitation. Each answer opens another chamber of silence, another door into the half-lit architecture of the real, where understanding grows not by ending wonder, but by teaching us how to carry it. What if the true lesson of broken physics is not that nature failed, but that our categories did? We began with confidence in walls that seemed immovable, past and future, matter and emptiness, object and observer, here and there. One by one, the experiments pressed against those walls until they turned porous. Not gone, not meaningless, but thinner than we believed. The universe did not descend into chaos. It revealed a subtler order, one that could not be understood through ordinary intuition alone. This is where science becomes something more than a collection of results. It becomes a discipline of self-correction, a way of noticing when our deepest assumptions have quietly hardened into blind spots. The most important experiments in physics were not always the ones that delivered immediate clarity. Often, they were the ones that introduced discomfort that lasted for decades, even generations. They left behind tensions, unresolved questions, and theories that worked beautifully while still feeling incomplete. In that unfinished space, human curiosity found its purpose. There is a certain courage in continuing under those conditions, to build a theory while knowing it may later be revised, to trust evidence even when it overturns the language that once made the world feel stable, to accept that explanation may arrive in layers, and that every deeper layer may ask us to become intellectually humbler than before. This is not weakness. It is the moral strength of science, the willingness to let reality remain larger than the mind studying it. And perhaps that is why these experiments matter beyond laboratories and equations. They speak to a universal human experience. Again and again, life teaches us that the world is not as simple as our first stories about it. People are more complex. Memory is less reliable. Time moves differently when we suffer, when we love, when we wait. What physics discovered in matter, we often discover in ourselves. That truth is real, but rarely shallow. So as this journey nears its end, one final question remains. When certainty fractures, what rises in its place? Fear sometimes, confusion often, but also something quieter and more enduring, a wiser form of wonder, able to stand in the presence of mystery without needing to flee from it. So where does that leave us? After all the paradoxes, all the delicate measurements, all the moments when physics seemed to step outside its own frame and look back at us, not at an ending exactly, more at a shoreline. Behind us lies the long confidence of human thought, the belief that with enough patience, the universe would become plain, orderly, and complete. Ahead of us lies something more demanding, and perhaps for that reason, more beautiful. A reality that can be known, but never reduced to simplicity. The experiments we have followed did not shatter science. They refined its character. They reminded us that truth is not always comfortable, and that the deepest forms of understanding often begin in disturbance, a strange pattern on a screen, a force emerging from empty space, a clock slipping out of sync, a particle crossing a barrier it should not cross. Each event was small in scale, almost modest in appearance. Yet together, they changed the emotional grammar of modern knowledge. They taught us that precision and mystery are not opposites. They can live in the same sentence. That may be the most human insight of all. We, too, are creatures of partial vision. We build stories to steady ourselves. We sort the world into categories so that it can be endured. But every life eventually encounters what does not fit: memory that shifts, time that stretches, absence that still exerts force, connections that survive distance, losses that are not as final as they seem. In that sense, physics has not drifted away from human experience. It has circled back toward it. So perhaps the final question is not whether the universe is stranger than we imagined. By now, that much seems clear. The deeper question is whether we can meet that strangeness with maturity, curiosity, and grace. Whether we can keep learning without demanding that reality becomes smaller than it is. Because in the end, the laws of nature were never truly broken. What broke again and again was our illusion that the world was built to match the limits of our intuition. And in that breaking, something lasting was given back to us. Not certainty, but wonder, deepened by understanding, and a humbling sense that truth is vast enough to keep calling us forward.